Okay, let's unpack this. Today, we're doing a really fascinating deep dive. It's about something fundamental in organic chemistry. How do you actually know what a molecule looks like?
Right, the structure determination puzzle.
Exactly. And we've got a great guide, Chapter 18 from Clayden, Greaves, and Warren's Organic Chemistry, the second edition. It's basically a big review of spectroscopic
The
methods.
really comprehensive one, yeah.
So our mission today is to, cut through the detail, pull out the key ideas, and really show you how chemists use tools like NMR and IR to solve these structural puzzles.
Think of it like chemical detective work.
Pretty nicely, piecing together clues the molecules leave behind.
And what's great about this chapter is how it pulls together threads from earlier parts of the book. It shows this deep connection between spectroscopy and how molecules actually behave, their reactivity.
So it's not just about identification.
Not at all. We're looking at how you combine these powerful methods, NMR, IR, mass spec sometimes, to figure out the structure of unknowns. And often it's done with, well, surprising elegance. This is practical stuff, solving real problems.
Okay, so where do we start our structural adventure? Our first case file, maybe? The chapter kicks off with a big one, the carbonyl group.
Yeah, C double bond O, absolutely central.
And it highlights how spectroscopy explains reactions, tells us about reactivities. So how do you distinguish, say, an aldehyde from an ester using these tools?
Okay, good question. If we need the big picture first, the most reliable way to separate the main carbonyl families, that's aldehydes and ketones on one side.
RCHO and R1COR.
Right. And then the acid derivatives, as esters, amides, acid chlorides on the other. The best tool for that initial split is 13C NMR.
Carbon NMR, okay. Why is that?
Well, it's down to the chemical shifts. The carbonyl carbons of aldehydes and ketones, they show up consistently in a specific window, roughly 91 to 215 ppm downfield. But the acid derivatives, their carbonyl carbons, are in a totally different range, typically 164 to 180 ppm.
So they don't overlap at all.
Exactly. Those two ranges are distinct. It's like a clear fingerprint. You see a carbonyl carbon signal, check the ppm value, and boom, if it's likely an aldehyde decatone or an acid derivative. It's a really powerful first step.
Okay, I see. Like the example they give, the keto acid.
Yeah, the saturated keto acid shows two signals, right? One at 208.4 ppm, that's the ketone, and another at 179.1 ppm, that's the acid. Clearly separated.
That's a fantastic starting point. But then, okay, say it's in that aldehyde decatone group. How do you tell those two apart? Because they react differently.
Right. For that distinction, 1H NMR is your friend. Proton NMR.
Okay.
Aldehydes have that unique proton attached directly to the cardinal carbon, the CHO proton, and it gives a very characteristic signal way downfield, usually between 9 and 10 ppm.
And ketones just don't have that proton.
Exactly. Ketones have two carbons attached to the carbonyl, no H. So if you see that 9-10 ppm signal, it's almost certainly an aldehyde. No signal there, probably a ketone, assuming your 13C data pointed that way.
Makes sense. Okay, so aldehydes and ketones are sorted. But here's where, for me, it got really interesting. The chapter says 13C-NMR is great for separating acid derivatives as a group.
Right.
But it struggles to tell the difference between different types of acid derivatives, like an acid chloride versus an ester or an abamamide, even though their reactivity is worlds apart.
Yeah, that's a key point. Their stereochemical shifts in 13C NMR, they all tend to bunch up in that same 164, 180 ppm range. It's not very diagnostic for distinguishing within that family.
So if 13C isn't the best tool there, how do chemists figure that out?
This is where infrared spectroscopy, IR, really shines. Specifically, you look at the C double bond bento stretching frequency.
Oh, the vibration.
Exactly. How strongly that bond vibrates tells you a lot. And it's governed by this interplay between two main electronic effects. You've got conjugation or resonance donation. Think of lone pairs on an adjacent atom, like oxygen in an ester or nitrogen in an amide. They can donate electron density into the CO pi system. This weakens the CO bond slightly, makes it easier to stretch, and lowers the frequency.
Okay, donation lowers the frequency. What's the other effect?
Inductive withdrawal. If you have an electronegative atom attached, like chlorine in an acid chloride, it pulls electron density away from the carbonyl carbon through the sigma bonds. This strengthens the CO bond, makes it harder to stretch, and raises the frequency.
So it's a balance between donation and withdrawal.
Precisely. Take acid chlorides. Chlorine isn't great at donating its lone pairs, but it's strongly electronegative, so the inductive withdrawal wins. That pulls the frequency way up to around 1815 cm.
Okay, high frequency for acid chlorides. What about amides?
Amides are the opposite extreme. Nitrogen is fantastic at donating its lone pair via resonance. That effect dominates, weakens the CO bond significantly and pushes the frequency down, often around 1650 centibar.
Wow, that's a big difference from 1850.
Yeah, huge difference. And esters, they're kind of in the middle. Oxygen can donate, but it's also quite electronegative, so they land around 1745 centibar.
Got it. So IR frequency is really sensitive to those
They're
neighbors.
very sensitive. And the chapter also shows how conjugation with other pi systems, like in an unsaturated ketone, also lowers the frequency compared to a saturated one. It mentions pent-2-enol versus pent-4-enol. The conjugated one is lowered by about 40 centibar a keton. It's all about how those electrons are spread out.
Okay, so electron distribution, conjugation, induction. But what if the molecule itself is physically strained, like bent out of shape? The deep dive reveals this other factor, small rings.
Yes, ring strain has a surprisingly strong effect on the CO frequency.
How does that work? It feels like strain should weaken things.
It's a bit counterintuitive. In small rings like cyclobutanone or cyclopropanone, the ring carbons can't achieve that ideal 120-degree angle around the cis-p2 carbonyl carbon. There's significant angle strain. This strain actually forces more p character into the ring bonds, which means more character goes into the CO bond itself. More character means the electrons are held tighter, the bond is shorter and stronger.
And the IR frequency goes up.
Exactly. It gets harder to stretch. So a typical six-membered ring ketone might be 1715 centimerai, but a five-membered ring is higher, around 1745 centimerai.
Plus 30.
A four-membered ring jumps to 1780 centimerai.
Plus 65 from the start.
And a really strained three-membered ring can be up around 1813 centimerai, almost like an acid chloride. And these effects add up.
Wow. And the penicillin example.
Yeah, the ball-actam, penicillin. That's a four-membered ring amide. Normally amides are low, like 1650, 1680. But in penicillin, that CO stretch is way up. It's 1777 error in the book, not 1715, reflecting that intense ring strain. It directly shows how much that four-membered ring is distorting things. Self-correction. Checking the source, the value for penicillin Wachtam CO is cited around 1780 centimeters 1 in many sources, reflecting the high strain. The initial value mentioned, 1715, might be for a different strain system or a typo in my earlier processing. We'll use 1770 for accuracy. Okay, checking that again, the value often cited is actually around 1770 centimeter for penicillin's beta-lactam carbonyl, much higher than an unstrained amide like a six-membered lactam at 1680 centimeter. That stark difference really highlights the impact of that four-membered ring strain.
Okay, 1770, even higher. That's dramatic. So ring strain screams out in the IR. Does it affect NMR too?
It does. The same idea about C character applies. Remember how small rings put more P character in the ring bonds?
Right, leaving more character for bonds pointing at.
Exactly. Like the CH bonds. More S character in a CH bond means the electrons are held closer to the carbon, which in turn shields the proton more effectively.
So the proton signal moves upfield, higher field.
Precisely. That's why protons on cyclopropane rings resonate at unusually high fields, typically 0 to 1 ppm, sometimes even negative values. Much lower ppm than the usual 1.3 ppm you'd expect for a CH2 group. It's a dead giveaway for a three-membered ring.
Huh, and that connects to alkynes too.
Yeah, it's a similar principle. Alkyne CH protons also appear upfield, around 2.5 ppm, even though the carbon is hybridized, which you might think would make it deshielded.
Right, spun usually means downfield.
But the high S character in that CH bond, plus the shielding effect from the cylindrical pi electron cloud of the triple bond, pushes the signal upfield. And you see it in the 13C NMR too. Alkyne carbons are around 60-80 ppm, much lower than alkene carbons.
Fascinating stuff. Okay, when we usually think about NMR splitting, it's proton coupling with other protons. But this deep dive goes into heteronuclear coupling different nuclei talking to each other.
Yeah, like protons coupling to fluorine or phosphorus.
So why these specific ones? Why are 19F and 31P highlighted?
Two main reasons. They're both nearly 100% naturally abundant, unlike 13C.
Oh, okay.
And they both have a nuclear spin of 1/2 I12, just like protons. This makes them NMR active.
Yeah.
I mean, they couple readily with nearby protons and carbons.
And these couplings can be big.
Oh, absolutely massive.
Yeah.
Especially the 1J coupling, so coupling across one bond. The chapter gives the example of dimethyl phosphite. There's a direct pH bond,
Right.
and the 1J pH coupling constant is 693 hertz.
693.
Yeah. On a typical NMR machine, say 250 millihertz, that means the proton signal isn't just a singlet, it's split into a doublet, where the two peaks are over 2 ppm apart.
Wow. That's unmistakable then.
Totally. It's a giant flag saying there's a proton directly bonded to phosphorus here. Same idea with fluorine. In fluorobenzene, the carbon directly bonded to fluorine, the ipso carbon, shows a huge 1 JFC coupling, about 244 Hertz, and you see smaller couplings to carbons further away too.
So, okay, if these couplings are so useful, why don't we routinely see, say, 13C1H coupling in our standard proton NMR spectra? It seems like that should be there.
It is there, technically, but you usually don't notice it. Yeah. In a proton NMR spectrum, remember that only about 1.1% of carbon atoms are the NMR-active 13C isotope.
Ah, the abundance issue again.
Right. Most protons, over 98%, are bonded to 12C, which doesn't have spin and doesn't couple. So the main peak you see is just from protons on 12C.
But the 1.1%.
The tiny fraction of molecules with a 13C at that position do show coupling. If you zoom in vertically on a strong, clean singlet in a proton spectrum, you can sometimes see very small peaks flanking it symmetrically. These are called 13C satellites. They're faint, but they represent that 1 JCH coupling.
Okay, I see. So they're usually just too small to worry about in proton NMR. What about in 13C NMR? Why are those spectra usually all singlets? We know protons are abundant.
Good question. In 13C NMR, the situation's reversed. You would see massive splitting from all the attached protons because the 1 JCH couplings are large, typically 100 to 250 Hertz.
So the spectra would be really complex.
Incredibly complex.
Yeah.
A CH group would be a doublet, a CH2 a triplet, a CH3 a quartet, all with huge splittings. It would be a nightmare to interpret just overlapping messes.
Okay, so how do we get the clean singlets we normally see?
We use a technique called proton decoupling. While recording the 13C spectrum, a second radio frequency transmitter irradiates the sample at all the proton frequencies. This constantly flips the proton spins, averaging out their magnetic effect on the carbons.
It sort of scrambles the proton signal.
Essentially, yes. It decouples the protons from the carbons, causing all that 1 JCH splitting to collapse. That's why a standard 13C spectra shows sharp singlets for each unique carbon. It simplifies things dramatically.
Makes sense. It's a deliberate simplification. Now, speaking of coupling, the chapter revisits proton coupling in cyclohexenes, how it tells us about axial versus equatorial protons.
Right, a classic application. Coupling constants are fantastic probes of stereochemistry, specifically dihedral angles.
The angle between the protons?
Exactly. In a cyclohexane chair, transdiaxial protons, one pointing straight up, one straight down on adjacent carbons, have a dihedral angle of about 180 degrees. This perfect anti-paraplanar alignment allows for maximum orbital overlap for the coupling interaction.
So the coupling is large.
Very large, typically 10 to 12 Hertz. If you see a coupling that big between two protons on adjacent carbons in a cyclohexane, it's a strong indicator they are transdiaxial.
And other arrangements, axial, equatorial, or equatorial.
They have much smaller dihedral angles, around 60 degrees. The orbital overlap is much poorer, so the coupling constants are significantly smaller, usually in the 2 to 5 Hertz range.
So just by looking at the splitting pattern and the size of the J value?
You can often assign the conformation. You can tell if a substituent is axial or equatorial based on the couplings of the proton on the same carbon. The chapter shows this with some cyclohexane esters. It's a really neat way to see the 3D shape.
This is all fantastic background. But the real excitement is applying it, right? Using these tools to solve actual unknowns. The chapter has some great examples.
Yeah, the case studies really bring it home, like the ambiguous reaction product 1. Adding hydroxylamine to an enone, you could potentially make two different isomers.
Where the N and O are swapped, basically.
Right. How do you tell which one you actually got? Well, the IR spectrum showed no NH stretch. That immediately rules out one possibility.
Wait, negative evidence.
Very powerful. Then the 1H NMR showed no alkene proton, but it did show a CH2 group signal around 2.6 ppm. Again, the absence of the alkene signal, combined with the presence of the CH2, pointed definitively to the correct structure. And you figured it out without even needing the reaction mechanism.
Clever. What about the reactive intermediate example, ketene?
Ketene, CH2ClO.
Super unstable stuff.
When you heat acetone, it can form a dimer, C4H4O2. Spectroscopy was key to showing it's a cyclic ester, a myolactone structure, not the symmetrical diketone you might guess.
How does spectroscopy show that?
The 1H NMR was complex, showing 3 types of protons with couplings consistent with the cyclic ester. Crucially, the 13C NMR showed a carbonyl signal around 185 ppm. That's firmly in the acid derivative range, not the ketone range, which would be over 200 ppm.
Okay, 13C points to ester.
Then they did ozonolysis, broke it down, and got an unstable intermediate. Its IR showed 2 carbonyl bands at very high frequencies, 1820 and 1837 more. This matched the expected values for a strained, 4-membered cyclic anhydride, calculated using those additive rules for ring strain we talked about.
Wow, linking it all together.
And the ultimate proof. Under careful conditions, they could detect monomeric ketene itself. Its unique IR absorption, way up at 2140 centimar, and its dead simple NMR, just a 2H singlet in the proton NMR, and 13C peaks at 194.0, and remarkably, 2.5 ppm for the CH2, confirmed its identity.
Amazing. And then there are those really unusual structures,
Yeah.
cubane.
Yeah, structures once thought impossible. Cubane, C8H8, a cube of carbons. Its structure was confirmed by its sheer simplicity in NMR. Because of the high symmetry, all 8 protons are identical, and all 8 carbons are identical.
So just one signal in each spectrum.
Exactly. A single sharp line to the 1H NMR at 4.0 ppm, and a single line in the 13C NMR at 47.3 ppm. That pattern is only possible for a structure with that level of symmetry.
It's like the lack of complexity is the evidence.
Precisely. They even use 13C NMR to distinguish between 2 other wild isomers, tetra-T-butyl cyclobutadiene and tetra-T-butyl tetrahedrine. The cyclobutadiene is unsaturated and has double bonds.
Right.
And it showed a characteristic 13C signal for those unsaturated carbons way downfield to 152.7 ppm. The tetrahedrine, being fully saturated, just has signals in the typical alkane region. Clear difference.
And finally, natural products from tiny amounts. The butterfly pheromone.
Yes, like Korea series, they had micrograms of this stuff. Mass spec suggested the formula C8H9ON. IR showed a carbonyl around 1680 centimar.
Okay, stereospecific.
Then the 1H NMR was the key decoder ring. No aldehyde proton. One methyl group signal. Signals matching a entity CH2-CH2 unit. And crucially, 2 doublets in the aromatic region with a small coupling constant, only 2.5 hertzes.
Small coupling. What does that suggest?
For aromatic rings, small couplings often mean the protons are further apart, like metacoupled, 1:3 relationship, rather than ortho, 2/2. Using that, plus known chemical shifts for pyrrole rings, they pieced together the fragments and identified the structure a specific acyl pyrrole. It's incredible what you can deduce.
It really is chemical detective work at its finest. Now, the chapter also provides all those useful data tables, chemical shifts, IR frequencies.
Essential reference tools.
But it also offers insight into interpreting them, especially comparing proton and carbon NMR shifts. Why is it often easier or maybe more reliable to predict proton shifts?
That's a subtle but important point. The chapter gives tables showing how electronegativity affects shifts, how functional groups influence nearby nuclei, but yet proton shifts are often more straightforward to interpret and predict using simple additive rules.
Why is that?
2 main reasons, really. First, the carbon atom is right at the functional group or substituent, while the proton is 1 bond further away. That means the carbon experiences more complex electronic effects, resonance, lone pair interactions, anisotropy, things that are harder to predict simply.
It's closer to the action.
Right. The proton, being a bit more removed, mainly feels the simpler through-bond inductive effects, which tend to be more additive and predictable based on electronegativity.
Okay, distance matters. What's the second reason?
It relates to how effects transmit. For 13C shifts, both the atom directly attached, alpha effect, and the atom next to that, beta effect, can have significant impacts, sometimes comparable in size or even opposite in direction. This makes simple predictions tricky.
So alpha and beta effects complicate carbon shifts.
Yeah. Proton shifts, on the other hand, are dominated by the alpha effect, and the influence drops off much more rapidly with distance. Beta, gamma effects are smaller. This makes proton shifts generally a more reliable, direct indicator of the electronic environment caused by nearby groups. You could often estimate them quite well just by adding up substituent effects.
So proton NMR, simpler, more additive, better for quick inductive reads. Carbon NMR, more sensitive to complex effects, maybe harder to predict simply, but gives direct info about the carbon skeleton.
That's a good summary. You need both, of course.
Yeah.
But understanding their different strengths helps you interpret the data effectively.
Well, that brings us towards the end of another, I think, really insightful deep dive. We've unpacked how spectroscopy, especially NMR and IR, is just fundamental to organic chemistry. It's the toolkit chemists use to see molecules.
Absolutely. From telling functional groups apart to sensing ring strain, finding fleeting intermediates, identifying complex natural products, they're indispensable.
You really can't do modern organic chemistry without them.
And stepping back, it's worth remembering that this precision, this ability to get hard data, is what allows us to test our ideas about structure rigorously. We don't just guess, we measure. It's how physical measurements truly unlock the secrets of the chemical world.
It connects the microscopic world to numbers we can actually see and interpret.
Exactly.
So next time you see a chemical structure drawn out, Maybe take a second to think about the invisible light waves, the magnetic fields, the vibrations that were likely used to figure out it actually looks that way. And it makes you wonder, what other impossible structures are out there, waiting for spectroscopy to help us find them?
That's the exciting part, isn't it? The exploration continues.
Keep digging into those chemical mysteries.